The internet is broken. No, not because of Kim Kardashian, because of Pierre de Fermat, or more accurately, an algorithm that he wrote down about 400 years ago for factoring large numbers. So everything from your private photos to state secrets relies on this particular kind of encryption called RSA encryption. RSA encryption works this way. You pick two prime numbers, you multiply them together, and you generate a product that you make public. And anyone in the world can use that number to encrypt a message and send back to you, but they encrypt it in such a way that only you, knowing the two original primes you chose, can decrypt and read the message. The only reason this works at all is because while it's very easy for you to multiply the two primes together that you chose, it's very hard for someone to take a look at the product of those two primes and work their way backwards to the original prime factors. Because whereas multiplying is easy, factoring is hard. Unless, that is, you're aware of this particular algorithm written down about 400 years ago. The algorithm works this way. Take roughly the square root of 8927. In this case, that's a little bit bigger than 94. And go to the next integer up. So we would assume, well, let's look at 95 squared. 95 squared is 9025. And so we want to figure out 9025 minus what number makes 8927. If that other number is itself a perfect square, we can rewrite 8927 using this difference of squares pattern. In this particular case, it's not. 9025 minus 98 would give us back 8927. So the algorithm didn't work with 95. But that's fine, we just move to the next integer up. Let's square 96 instead. 96 squared is 9216, and 9216 minus 289 does make 8927. And if you know your squares, you know that 289 actually is a perfect square. It happens to be 17 squared. This is going to give us a non-trivial factorization of 8927. Specifically, that 8927 is the same as the sum 96 plus 17 times the difference 96 minus 17. That just so happens to be 113 times 79. Now this does not mean that the encryption that depends on this kind of prime factoring is broken in general, but it does mean that it's broken anytime the two underlying primes happen to be somewhat close together. If those two primes are somewhat close together, then you could use this algorithm to factor out really large odd numbers much more quickly than you would expect, simply naively beginning at 3, 5, 7, 11 and going on and checking all the prime numbers. So there you have it. If you're struggling through 8th or 9th grade algebra, or you remember struggling through 8th or 9th grade algebra, just know if you had memorized your difference of squares pattern, you could be cracking into iCloud accounts right now. Not that you would, of course, but it's nice to know that you can.